This is first of the 5 experiments done with the company Milgo-Bufkin. It spanned from 1997 to 2004. The goal was to make infinite variations from unified morphology using one material, metal in this case, and one method of fabrication, curve folding, to make fluid 3D forms that are stronger and are made from flat sheets using available technologies like laser cutting, water jet cutting, and other methods. There was considerable interest from the company in future methods like robotics, including making machines. The method of curve folding was applied to architectural elements, columns, walls, ceiling panels, windows, doors, curtain wall systems, curved truss, curved standard sections, architectural environments, and furniture design. The thesis for a unified morphology is that all forms and variations can be mapped in higher dimensional space, a hypercubic lattice in this instance, where each change in form is specified along an independent direction of this space. The directions combine with each other, so all changes and all combinations of all changes can be systematically and exhaustively mapped in this space and indexed by higher dimensional Cartesian coordinates. Further, each change is continuous as shown in the animations on the right. The diagram captures a form continuum. Each form in space is a frozen moment in time. Examples of full-scale curve-folded columns showing 6 frozen moments from a vast inventory of possibilities obtained by folding flat metal sheets. All are developable surfaces obtained by intersection of cylinders and controlled by various parameters like radius of cylinder, angle of intersection, height and width of intersecting curve, number of waves, and so on. The one on the left, the simplest, has convex folds, followed by next two with star sections, one with half wave and the other with a full wave in elevation. The fourth one from left has offsets between the folds. The fifth one shows the beginning of asymmetry. It's in the spirit of Nervi's ribbed columns, hair folded from a single sheet of metal. Finally, full asymmetry on the right, starting with symmetrical fold, achieving symmetry breaking from the same method was an achievement. Here are the many variations we made. Left shows a photo montage of various columns. Top right shows a collection of mini columns. Bottom right is from an exhibition at a gallery, and the middle bottom shows a series of 4 columns in titanium commissioned by the Museum of Modern Art, New York, for their permanent collection. This was the first time titanium was curve folded. Wall and ceiling panel systems using the same method of curve folding. The simplest ripples on the left. Next is a wall system with cascading 90-degree bends and a stepped section. Next is a wall system with alternating 90-degree bends and a rectangular wave section. On far right, the 2 drop-in panel systems with continuous wavy angles. Making wavy angles was a surprise and marked the beginning of inventing structural elements by folding flat sheets. 3 more panel systems, top left from 4 nested panels, bottom left from 2 longer nested panels, and a folded surface from a single 8 by 4 foot metal sheet with a different method of fabrication. Simple and complex ripple systems reminiscent of sand and water ripples. The one in the middle is made from a limited number of modules that could be reconfigured like pattern tiles. The same system permits simple ripple patterns on bottom left, or the slightly more sophisticated version on the top right. Animation on top left shows variations by changing widths and heights. The wavy angle system we saw earlier can be repeated to make wavy versions of standard alphabet sections. The truss on left has rectangular box section made by joining 2 L's to make a rectangle. Similarly, 3 L's make a L-shaped section, 4 Ls make a T section or a U section, 6 Ls make an I section. These lead naturally to curtain wall systems and window frames. Additional curtain wall systems and window panels with wavy framing members. The morphing beam in red color on left is a fixed beam which has acquired notches for receiving panels. 2 square window frames, middle left, the top one made from 4 cantilever-shaped beams and the bottom one from 4 simply supported beam shapes. One of them is arrayed into a curtain wall system on top, middle, and then applied to an exterior of a building in New York City on far right. And at the bottom is a 3D cubic space frame based on the same idea. The curve folded surfaces can be used to make usable space and define an environment. 2 different gallery designs are shown. Gallery 1 has a stepped pixelated section from a single folded surface that is mimicking a curved profile by zigzagging. Gallery 2 has a steeper irregular folds and can be built from bays, shown on bottom right, which are bound by structural flanges, green, which enable joining with adjacent bays. The animation here shows a portion of the irregular surface as a reminder that these could be future possibilities when we'll have new materials that can enable such morphing. And in the last slide shows the irregular wall system we call hyperwall. It's a double wall curved folded panel system that can be used as modules. These modules fit together and you can keep making different compositions like the ones on the left, which is a walkthrough environment. One on the bottom right is an irregular bench for a student lobby in Rutgers. And on the top right is the animation of a portion of the hyperwall system. The idea again in future, maybe new materials might enable to make curved surfaces joined with morphing seams as hinges. As of this point, we don't know how to make them. In summary, one fabrication method of curve folding did produce a variety of morphologies in different scales by continuous changes in form to achieve infinite variability. This led to the first example of mass customization of industrially produced architectural products. The work continues to be inspired by nature, where form, material, and process are one, unlike the structures that we build. There are many people to acknowledge. Bruce Gitlin, the most important one for providing the opportunity and the factory for these experiments. For fabrication, the main person, Alex, and with his support. And for computer modeling, again, main person, Neil Katz, in fact, the only one. Animations by Seve and Brian, renderings, Ajmal and Seve, and photography by Robert and Bruce. Thankful to NISTA for the support and the students who helped with building that curved truss and some of the prototypes for the curtain wall systems. And to Pratt Institute, several people, all of them continuing support for a long period of time, and the studio itself. Thank you very much.